Thank you, John, for agreeing to take on this task. Our speaker today is our old friend, John Axe. John is a distinguished physicist. He did his undergraduate work at the University of Denver and then got a PhD at Berkeley. And from Berkeley, he went to something that may not be open anymore. I don't know, but he went to work for IBM when they were sponsoring, not that IBM is not open, but all these big corporations used to have really wonderful fundamental laboratories like Bell Labs. And with the changes in laws and things, it made them impossible for these corporations to maintain this effort. Anyway, John was with IBM for 7 years, and then he moved to the Brookhaven National Laboratory on Long Island, way out on Long Island, I can tell you, where he worked with neutron diffraction, among other things. He became the head of the neutron diffraction device. What was it, a synchrotron, cyclotron, something that shot out neutrons and bombarded the targets. And he became the scientific director of that device. And then somewhat later, but concurrently, he also was made an associate director of the Brookhaven Laboratory. And then I guess in 94 or something like that, he retired. He came to Florida first. And then the attractions of Oak Hammock got to him, and he and Janet moved here. So we're delighted to have him. This particular prize is described by the Nobel Committee as complex. And that's all they said about it. They didn't really explain anything about it. And when I saw that, I said, well, it's only one guy who's up to giving us a lecture on this sort of topic. And John, after a little bit of arm twisting, very graciously agreed to do it. So thank you very much, John, and we're waiting to hear what you have to say.
Thank you, Ken, for that overly generous introduction. Is my mic okay? Everybody hear me okay? All right. Yeah, this is an interesting Nobel Prize. It was given to 3 physicists for independently performing experiments aimed at clarifying the underlying puzzle of quantum mechanics, which Einstein called spooky action at a distance, and which we'll talk more about. John Clauser, now 79 years old, worked at Lawrence Laboratory at Berkeley, where I was at one time. Alan Aspect, who's now 74, worked at the University of Paris, and in 1981 did more refined experiments using particles of light to work on this problem. And Anton Zeilinger, who's now 77, did further clever and really difficult experiments with various collaborators over the past 20 years. And it's worth commenting that this recognition came many years after Clauser and Aspect did their experiments, and that all 3 are now in their mid to late 70s. I don't completely understand the details of most of these experiments, but I want to begin by telling you about the history of the development of quantum mechanics, and then explain what spooky action at a distance is, and to tell you that although these experiments confirm its existence, there is still no accepted understanding of it. Isaac Newton taught physicists how to understand the motion of large objects like the moon around the Earth, or a fly ball to center field, or even the motion of something as small as a single biological cell. If you know the mass and the velocity of an object and the force that's acting on it at one instant of time, you can calculate the position and velocity at a later time. Repeat that calculation over and over again, and you can deduce the entire trajectory. But a typical biological cell contains about 100 trillion atoms. And by the beginning of the early 20th century, experiments had begun to show that Newton's prescription didn't work for motion of individual atoms. And a bunch of Nobel Prizes went to the founders of atomic physics. So let's begin briefly by reviewing them. In 1909, Ernest Rutherford, who was a Cambridge-educated physicist from New Zealand, showed that a beam of alpha particles, which are the nuclei of helium atoms, were deflected at very large angles in passing through a very thin gold foil. And he concluded that this showed that most of the mass of the atoms must be contained in heavy, positively charged nucleus that's surrounded by much lighter electrons that are necessary to make the atom electrically neutral. This gold foil experiment was clearly Nobel Prize caliber, but he had just gotten a Nobel Prize in chemistry the year before for his earlier work in radioactive decay. Max Planck, at age 60, got the 1918 Nobel Prize for showing that the wavelength distribution of light emitted by a heated object could be understood if the light was thought of as a particle rather than a wave, and that each particle had an energy that was proportional to the frequency of the light when it was thought as a wave. The proportionality constant, H, needed to fit the data is today known as Planck's constant. When he published the result, he admitted that this was puzzling. Planck was an outspoken pacifist who had a very sad personal life. He had 4 children. 2 daughters died in childbirth. 1 son died in Verdun at World War I, leaving 1 youngest son who was executed by the Gestapo for plotting the assassination of Hitler. And then his home was destroyed by Allied bombs in the final days of World War II. But all through that time, he shielded many Jewish collaborators and their families from execution. He was a wonderful man. Well, you all recognize this man, Albert Einstein. He's most famous for his theory of special relativity, which he developed in 1905 and which revised our understanding of the nature of space and time. But for nearly 2 decades, his nomination for the Physics Nobel Prize for this work was blocked by a series of Nobel committees for reasons that still remain unclear. His only Nobel Prize was given in 1921 for his prediction that if, as Planck said, light was a particle with quantized energy, then the electrons emitted when light strikes certain metals, the so-called photoelectric effect, light strikes the metals, knocks out electrons, also carried this same quantized energy. And it was shown later that that was the case. A year later, the Danish physicist Niels Bohr was given the Nobel Prize for his model of the atom, in which electrons bound to Rutherford's heavy nucleus were given in energies quantized by the same units proposed by Planck for light and by Einstein for unbound electrons. The electrons orbited around the positively charged nuclei like planets around the sun. And for the simplest element, hydrogen, the model correctly predicted the frequency of the light needed to move a single electron from one allowed orbit into another one. This is the model that is first presented to students today in understanding the periodic table of the elements. Louis de Broglie, born to a French aristocratic family, postulated that since Einstein had shown that the wave-like light sometimes acted like a particle, then particle-like electrons and atoms might return the favor and sometimes behave as waves. Well, physicists can make theories, but it's the job of experimentalists to devise experiments to test them. How could de Broglie's idea be tested? Well, it had already been established about 100 years before that when a beam of well-collimated light was shown on two closely spaced slits, the pattern on the screen behind was wave-like, with light from each slit spreading out in a way that was brightest, not between the two slits, but between them. I'm showing you that here. Light comes in. The light is not most prominent here and here, but between the two. This is a similar pattern that's seen with water waves. So that gives you the idea of how you can do that with smaller particles and maybe see the same thing. De Broglie was awarded the 1929 Nobel Prize in Physics only after both an American physicist, Clinton Davison, and a British physicist, George Thomson, independently demonstrated that electrons in a two-slit experiment, like the one I just showed you, did indeed produce the same wave-like diffraction patterns. Davison and Thomson waited 8 more years for their shared 1937 Nobel Prize for this work. Werner Heisenberg was awarded the Nobel Prize in 1932 at the very young age of 31. His great contribution was to embrace particle wave duality and to show that this implies that it's impossible to simultaneously precisely measure both the momentum and the position of a particle because their product must at least always be a small but finite number, again involving Planck's constant. That's this relation shown here. Why is this so? Well, one way to pin down the position of a single electron is by bouncing light off of it. And for that, the shorter the wavelength of light, the better. But light also has momentum, and the light-electron interaction will alter the momentum of the electron. So that long wavelength light changes the electron momentum less, but it more poorly localizes its position. Unlike Einstein and some other physicists, Heisenberg, like Planck, elected to stay in Germany after Hitler came to power. He was the principal scientist in the German nuclear weapon program during World War II. He was also instrumental in designing the first German nuclear reactors, but he told the German High Command that a nuclear weapon was not feasible. Well, Bohr then incorporated the Heisenberg uncertainty principle into his model of the atoms by stipulating that only electron orbits that satisfied this principle were allowed, and that they emitted or absorbed energy only in quantized steps. And conservation of energy explained why the energy of the light emitted or absorbed was also quantized. Erwin Schrödinger was awarded the 1933 Nobel Prize at age 46. He was born and educated in Austria and replaced Max Planck as the physics professor at Berlin before moving to Dublin in 1933. His mother was Irish. But he moved because of his hatred of the Nazi influence, and there he established an Institute for Advanced Studies. In 1926, he developed an equation that has been universally celebrated as one of the most important achievements of the 20th century, and which is universally known as the Schrödinger wave equation. In high school physics courses, you learn about atomic physics and chemistry using the Bohr model of the atom. In an advanced college physics course, you learn to describe the atom using the Schrödinger wave equation. This is the most mathematical equation that I'll show you. The left side of the equation represents the rate of change of this Schrödinger wave with time. And the right side is the sum of the kinetic and potential energies of the wave at one specific time. This is called a differential equation, and this form is familiar in classical physics problems. I would like to show you a little more using a simple problem that everyone encountering the Schrödinger equation for the first time must puzzle over. It concerns an otherwise free particle of mass m enclosed in an infinitely deep one-dimensional box of length L. The allowed wave functions are simple sinusoidal waves that exactly fit inside the enclosure, and they are characterized by the integral numbers, n equals 1, 2, 3, and so on. And the allowed energy levels increase in proportion to n squared. And notice that the lowest allowed energy, wrong thing, sorry. The lowest energy here is not zero, because a quantum particle cannot be at rest, because then its position would be well defined, which would violate Heisenberg's uncertainty principle. The Schrödinger equation is all you need to explain precisely the observed energy levels of hydrogen atoms until you put them into a magnetic field. Then each level splits into two levels with a spacing that grows with the increasing magnetic field strength. This happens because each electron behaves like a tiny magnet, with poles aligned along the field direction. Experimentally, this much was known even prior to Bohr's first model of the atom, and it allowed him to deduce the value of the magnetic pole strength from the magnitude of the splitting. But a theoretical understanding of this behavior in a magnetic field required a treatment involving Einstein's theory of relativity. The first person to tackle that calculation was the English physicist Paul Dirac. He deduced this wonderfully simple equation for the value of the dipole moment. It's just the product of the electric charge times Planck's constant divided by 4 pi. That earned him a share of the 1933 Nobel Prize with Schrödinger. And for many years, this value was in satisfactory agreement with the experiment. But by the late 1940s, theorists had realized that there should be smallish corrections to Dirac's expression, which occurred because while in the magnetic field, an electron has a small but non-zero probability of emitting and then quickly reabsorbing one or more photons. The American physicist Julian Schwinger did the first one photon correction in 1948. Then both the Japanese physicist Tomonaga and American physicist Richard Feynman discovered easier ways to do the calculations. And over the course of several years, Feynman extended the accuracy of Dirac's answer by an 11 decimal point correction to the Dirac result. That earned the three of them a share of the 1965 Nobel Prize in Physics. Incidentally, an error in one of Tomonaga's calculations was found and corrected by a future Oak Hammock resident. His name was Charles Summerfield, who was then Yale physics professor. Now, there was a clear motivation for experimental physicists to improve the measurement of the magnetic moment. Using new microwave equipment invented during World War II, two American physicists, Polycarp Cush and Willis Lamb, working independently, took the challenge, and their observed values were in quite good agreement with the new calculations. That earned them a share of the 1955 Nobel Prize. But how good was quite good? The two numbers differ by 3 in the last decimal place. If you were to measure the distance from Los Angeles to New York with that accuracy, it would be off by about the thickness of one human hair. Notice that the prize for the calculation was not given until 10 years after the experiment confirmed their correctness. It would have made sense to give the prize for both experiment and theory in the same year, but I think the custom at that time was not to split the award more than 3 ways. And John, maybe you know whether that's still the case or not. Okay, so far I've tried to tell you about some of the strange dual wave particle behavior of individual atoms and other subatomic particles, and of the physicists who over some 30 years have won Nobel Prizes that studied them. To recap, the rules of classical physics are well established and work well for large objects which are massive enough that Heisenberg's uncertainty principle is no practical restraint to knowing both their position and momentum at a given time. But for particles of light and single individual atoms and molecules, the rules are different. And these rules work perfectly well and even show how, as objects get bigger, the rules simplify toward the classical ones. So learning to use the Schrödinger equation is all that most practicing atomic physicists need to know. But there were deep philosophical questions about something called quantum entanglement that didn't satisfy some physicists, including Schrödinger himself, and particularly Einstein, who called it spooky action at a distance. So what is quantum entanglement? I'm going to show a portion of a YouTube presentation made by Don Lincoln, who is a particle physicist working at Fermi Laboratory, to explain, because he has some very nice graphics to go with it.
sizes as big as people or even larger. So just what is quantum entanglement? In an earlier video, I talked about how the behavior of a subatomic particle, like a photon or an electron, is described by what is called a wave function. Brushing over many details, the wave function governs the probability that you will find the particle in a particular configuration. Before you make a measurement, you can't know, even in principle, what configuration the particle is in. To give a concrete example of what I mean by the word configuration, let's use the direction of the spin of a particle. Now, there is a quantum weirdness in that when you measure the direction of the spin of a particle, you first have to pick a direction, and then the outcome will always be either in the direction you picked or exactly opposite. It can't be anywhere in between. So, if you picked a measurement direction to be horizontal, the measurement of the spin direction could be left or right. It couldn't be up or down, forward or back, or any direction except for right or left. On the other hand, if you decided to measure in the vertical direction, the only outcomes of your measurement would be up and down. Left and right would be forbidden. It's certainly counterintuitive, but it's just a weird fact of life in the quantum world. Now, prior to the measurement, the wave function might say that the spin axis of the particle could be in any direction. Indeed, the most popular understanding of quantum mechanics says that the spin direction actually is in all directions allowed by the wave function. It's only when you make a measurement that the wave function collapses and the outcome becomes real. If you'd like some more information on wave functions and how they collapse, that other video might help. Now, what would happen if you had two subatomic particles? If you're like me, you'd think that they'd both be governed by an individual probabilistic wave function, and they'd be totally independent, with the spin direction of one particle having nothing to do with the spin direction of the other, and both of them being in all directions until a measurement is made. And that happens with four possible outcomes: two wave functions and two probabilities with all combinations of up and down. However, it's possible to prepare two subatomic particles so they both are described by a single wave function. That's what we mean by entangled: two particles and a single wave function. You do this by taking a parent particle, which in our example has zero spin, and let it decay into two particles. Spin is a conserved quantity, which means that it can never change. So if the parent particle has zero spin, then the two daughter particles have to have opposite spin. If one has a spin pointing left, the other is right. If one is up, the other is down, and so on. When you add the two, you get the zero that you started with. So that's the simplest example of a pair of entangled particles, which is to say two particles with opposite spin and a single wave function that governs both of them. Okay, so now we're getting somewhere. The entanglement doesn't depend on the two particles being close to one another. As long as the two particles don't interact with anything, you can separate them by feet, miles, or even huge distances, and the two particles are connected by a single wave function, and the two particles will have opposite spin. Now, remember that one of the key facets of quantum mechanics is that the quantum world is intrinsically probabilistic. We can't know, even in principle, the outcome of a measurement before we make it. So, suppose we select one of the two particles and pick a direction to measure the spin. Say we pick horizontal. The measured spin will be either right or left, each 50% of the time. We could have selected the other particle to do the measurement with the same result, 50% right and 50% left. The real weirdness arises when we measure the spin direction of both of the entangled particles. Say we measure the horizontal spin direction of this particle over here on the left, and the measurement says it's to the right. Then we know that the outcome of the other measurement, it will be 100% of the time left, 100% of the time. That means that the information that one of the two particles had a measurement made on it was transported to the other particle, And here's the spooky thing. We can measure the spin direction of the two particles in quick succession so quickly that we measure the second one before any conceivable information from the first measurement could have arrived. Let's be super concrete on this by remembering that the fastest thing in the universe is light. It travels a foot in a billionth of a second. Now, let's take two entangled particles and separate them by 10 feet. It will take light 10 billionths of a second to travel from one to the other. So now let's get tricky. We'll measure the horizontal spin of one of the two particles and see that it's to the right. Then, 5 billionths of a second later, we measure the horizontal spin of the other particle. We find 100% of the time that it's to the left. And remember that we did it so fast that not even light could have told the second particle the outcome of the measurement of the first particle. That means that quantum information can travel faster than light. Yeah, you heard me right, faster than light. That blew Einstein's mind, too. In fact, he co-authored a paper in 1935 with Boris Podolsky and Nathan Rosen that highlighted this problem. He also called this transfer of quantum information spooky action at a distance. This was one of many reasons why Einstein didn't like quantum mechanics. So what do we think about this phenomenon today? Does quantum information move at speeds faster than light? Yeah, it seems to. But it doesn't invalidate Einstein's theory of relativity because we can't control it. We can make both measurements and the outcome will seem random, and we'll only know that the two were opposite when we compare the measurements, and that information can be transferred no faster than the speed of light. So that saves Einstein's theory, which is a relief. Otherwise, I'd have to learn a whole new bunch of physics. But it's still perplexing. How is it that quantum mechanics can travel so fast? Well, there were some people, including Einstein, who thought that this wasn't so mysterious after all. Suppose that you had a red and a blue ball, but you couldn't look at them. You grab both of them and put them in boxes and separate the boxes. Later, you look in one of the boxes and see that it contains a blue ball. It will surprise nobody that the other ball is red. The answer was determined at the moment the balls were put in the boxes, not when the first ball was observed. And I admit, when I first heard about this, that was pretty much my reaction. The technical name for this more ordinary connection is called hidden variables. So the question is, how do we know that there is something new and different about quantum mechanics? How can we test the idea of quantum entanglement and compare it to the more intuitive idea of hidden variables? There's a long history of this, with a prediction in 1964 by theorist John Bell and a test in 1981 by Elaine Aspect, as well as contributions by many others. I'm going to forgo the history and the details of the mathematics of the predictions and just explain the measurement. We know that if we measure the spin direction of one particle, that the other one will be in the opposite direction. But let's change it up. Suppose that we measure the spin of the second particle in a totally different direction. How does that change things? Let's measure the direction of the first particle in the vertical direction, but the second one in the horizontal direction. That means that when you measure the spin of the second particle, it will be either right or left. That's weird, but remember, that's how this works for quantum spin measurements. Now, I'm going to simplify the discussion by only talking about the situation when the spin direction measured for the first particle is just up. We could be more general and include both up and down cases, but it's more confusing, and the answer is absolutely identical. If you want to do the general case, let me invoke the phrase that physics professors love and students hate, which is, the exercise is left to the student. Okay, now let's get into both the quantum and hidden variable predictions. The first measurement is in the vertical direction, and it finds the particle has spin up. When you measure the spin of the second, you measure it in the horizontal direction, and you get right and left with equal probability. The first measurement gives you zero predictive information about the second measurement. It turns out that both quantum mechanics and hidden variables make the same prediction for this scenario. This is very different from if you made the second measurement in the vertical direction, because if you did, you'd get a second measurement in the downward direction 100% of the time. Again, this is the same for both quantum mechanics and hidden variables. So now we're ready for the final bit, which is to look at all possible measurement directions for the second particle and see if the predictions are different for quantum mechanics and hidden variables. We will still assume that the spin direction measurement for the first particle is upward, and then measure the spin direction for the second particle, starting upward and then slowly spinning the measurement through 360 degrees. This graph shows the predictions of how often the second measurement will be in the direction the second arrow is pointing. If the second arrow is pointing upward, we know that the second measurement is always downward. So that means the second measurement agrees 0% of the time. If the second arrow is pointing at 90 degrees to the right, the second measurement can be right or left with equal probability. So it will be to the right only 50% of the time. If the second arrow is pointing downward, we know that the second measurement always is downward. So it is in that direction 100% of the time. And as we go to 360 degrees, the pattern is reversed. It's very important that we see that the predictions from hidden variables in quantum mechanics are different. This is key. So those are predictions. What does a measurement say? Well, these black dots show the measurement, and they are quite definitive. Quantum mechanics is correct, and the whole idea of hidden variables is completely ruled out. So, what does this mean? It means that the idea that the final measurement is already determined at the moment the two particles is entangled is false. It means that when you measure one of the two particles, the quantum information is transferred to the other particle at a speed faster than light. Now, with
Okay, thank you, Julie.
such a
So, as Don Lincoln explained, a peculiar property of quantum mechanics is entanglement. If two photons, for example, become entangled, that is, they're allowed to interact initially in a very clever way, they will be defined by a single wave function. And even though they are separated, they will share that wave function. And measurement of one will determine the state of the other. Since the Schrödinger equation explains very well the probable measurable behavior of atoms and molecules, which is what most physicists want to know, they don't worry about how or why quantum entanglement works. But as Don Lincoln explained, Einstein, Podolsky, and Rosen introduced a thought experiment to argue that quantum mechanics was somehow a not complete physical theory. Einstein believed that these two entangled particles must have some unknown intrinsic property, which they called hidden variables. In a letter to Niels Bohr, Einstein famously wrote, "God does not play dice with the universe." What did Einstein mean by that statement? First, understand that the adult Einstein, whose parents were devoted Ashkenazi Jews, was by that time an atheist. So he may have been showing that he felt deeply that natural laws could not be like the throw of a dice. And he felt also that we should be trying to discover what that hidden property is. And he went to his death unknowing of the answer. Realized that it was only after John Bell discovered a way to actually experimentally check whether or not this rather vague hidden variable suggestion of Einstein's was correct that other physicists began to think about ways to perform experiments that have led to these 2022 Nobel Prize awards. In 1972, 8 years after Bell's paper, John Clauser, working together with a graduate student, Stuart Friedman, were the first persons to perform such a test. Clauser said that Bell had encouraged him to do this experiment, and Bell, was slightly disappointed that the no hidden variable result was that no hidden variables was the result. On the other hand, Clauser once corresponded with Richard Feynman, who told him that quantum mechanics is obviously correct and you're wasting your time with further testing. Here's what Clauser says now. If you prove something that everyone already thinks is true, and you're the first one to do it, you may not be recognized for 50 years. So my claim to fame is that I have lived long enough. And arguably, Friedman missed a shared Nobel Prize because of dying too soon. Now you might ask, why did John Bell not at least share the prize? That would have made a three-person prize. He reportedly had been nominated for a Nobel Prize as early as 1990, 32 years ago. But he died unexpectedly of a cerebral hemorrhage that year at age 62. So almost certainly, Bell also missed the Nobel Prize because he also died too soon. Okay, here we go. Now I want to show you something else that's sort of spooky. Consider how a glass prism bends light depending on its color. Why does this happen? Think about this as an analogy. A lifeguard from his chair at position S sees a swimmer in trouble at position D. He can run faster than he can swim, and his best choice is not the shortest distance path, nor is it the upper path of least water. It is, in fact, a path intermediate between those. It's the path of least time. That's also what a light ray does. When it travels from a fast medium like air into a slower medium like water or glass. And a prism separates light into different colors because red light travels faster in glass than blue light does, and therefore it bends less. I don't know how lens makers who understood this for nearly 3 centuries before thought about this, but I don't know if anyone else has used these words, but it is spooky why and how a light ray knows how to do that. Now quantum mechanics explains that, well, this is simply the most probable path. Alan Aspect and Anton Zeilinger did further more precise experiments than Clauser was able to do, letting the distance between the entangled pair of photons increase and probing for possible loopholes. Aspect was able to devise a mechanism that switched the direction of the entangled photons after they had been created and emitted by their source. And that eliminated the possibility that information about some filters in his device were communicating with one another. And Anton Zeilinger later conducted a number of further tests of Bell's inequality. He found a way to create entangled pairs of photons in a fiber optic cable and transported them over much larger distances. And he used random numbers to shift between the measurement settings. In one experiment, he used signals from a distant galaxy to further ensure that the signals could not affect one another. Most physicists today still regard action at a distance paradox as an illustration of how quantum mechanics violates classical physics, rather than as evidence that quantum theory itself is fundamentally flawed. But the Einstein paper did help deepen our understanding of the quantum mechanics by exposing fundamentally non-classic characteristic of the measurement process. The paradox shows that a measurement can be performed on another by distant entangled particles. Today, quantum entanglement forms the basis of several cutting-edge technologies. In quantum cryptography, entangled particles are used to transmit signals that cannot be intercepted by an eavesdropper without leaving a trace. I have read that these quantum cryptographic systems are already being used by major banks. And the oncoming field of quantum computation uses entangled quantum states to perform computational calculations in parallel, so that some types of calculations can be done much more quickly than others, much more quickly than they could ever be done with classical computers. So that's the story of how quantum theory has evolved over the years and has generated Nobel Prizes for 16 scientists over a period of 114 years. And there is still no agreed explanation of Einstein's spooky action at a distance. So thank you for listening. If there are questions, I'd be happy to try to answer them.
It's interesting that in this morning's Gainesville Sun, there is a picture of an event at Florida State University where they unveiled a statue of Dirac opposite a building that had just been built with his name on it. And this is kind of cute because Dirac did all his early work at Cambridge, but he came up against a hard retirement requirement at age 65, and he wasn't really ready to quit, but he had to find some place that would hire somebody who was older than 65. And of course, we're better than the state of Florida for that kind of thing.
Yeah, I once visited Florida State and got to shake the hand of the great man. He was a man of few words, and I shook his hand, and we left one another without saying a word. So.
Yeah, so he was an odd character, and his wife or his daughter was quoted today as saying, he got much better actually after he came to Florida. At Cambridge, he would never talk to anybody, and he wouldn't talk about his colleagues. When he came to Florida State, he began to ease up and became friendlier. And it was actually quite close to one of our physicists here at the university named Pierre Ramon. And I think they became actually pretty good friends. So there's a local touch, in a sense, to all of this. Larry.
I remember when the century turned, the American Physical Society. What? Okay. They said they had a goal of solving the deepest mystery of quantum mechanics by the year 2010, and apparently they didn't. Is that still a goal as far as you know? I think regarding entanglement.
Well, certainly I think people are continuing to, there's a certain small group of people that are working on this problem and have different ideas. Both theorists and experimentalists have different ideas about what might be a solution. But so far, there's been no, I don't think any real breakthroughs in that.
John, maybe John X, turn the microphone a little bit more toward your mouth.
Oh, sorry.
You can hold it too if you'd like.
Yeah, okay.
So you mentioned, is Zellinger, is that his name? I've forgotten the.
Zeidinger
Zeidinger said he compared one of the entangled particles in a galaxy, you say. Or,
No, that's not quite right. He's transported entangled particles. At least he's based in Vienna, and he has transported them at least across the Danube.
The Danube.
Into
Well, that seems.
But he has used signals from distant galaxies
Oh, I see.
to make switches in his.
So there are limitations in computers because the speed of light is still, even on small disks, a limitation. So this use of quantum events used for calculation, does that get around the speed of light limitations somehow? I know I'm asking a practical question because I don't really understand quantum physics at all. But is that, I mean, why they're looking into calculating using quantum, and is it to get around what kind of limitations are they getting around? The speed of light limitation or what?
Let me see if I know enough to explain a little something about how quantum computers work. Normal computers use silicon chips, which are basically on and off. Each silicon chip is an on or off device, two states, plus or minus, on or off, whatever, two states, zeros and ones. But quantum computers are built around components called qubits, which also have 0 and 1 states, but can exist in superimposed states. And they can even be entangled with other qubits, making them much more powerful than classic bits for certain computations. The problem is that these computers have to be kept at a temperature near absolute zero. So these are very tricky computers to use. But for example, do you know about the traveling salesman problem in mathematics? A salesman has to go through several, say 30 different cities and at different distances. And the question is, how do you do this in the smallest amount of time? It turns out that normal computers can, for let's say 30 cities, can work for several days to get the answer. The IBM has shown recently that their quantum computer can do it in seconds.
Amazon does it all the time.
Right. Any other questions? Yes. Phyllis.
as an economist, I'm familiar with simplifying assumptions. And I wonder if there are some simplifying assumptions underlying quantum mechanics. For example, the appearance of the factor 4 pi in two equations, separate equations. What's with this 4 pi figure?
Well, the 4 pi came from a rigorous calculation by Dirac with no assumptions in it, assuming that there was nothing happened between these two particles before you measured them. But then, as I tried to explain, people realized that those particles could be interacting with other particles and changing into other particles. And so that's when they had to do these other calculations. These other calculations are also rigorous. It's just that it's an infinite series of such calculations. And they've now gotten up to, I don't know, 22 terms or something like that. And as you see, the two numbers agree almost perfectly, right?
Years ago, in a course on physical organic chemistry, which I didn't understand at all, there was an approach to doing quantum chemistry while lying in a hammock. In other words, apparently there were some real calculational shortcuts one could take and discover quite a bit about the quantum chemistry involved. But I can't remember any of the details of how you were supposed to do that.
Yeah, it's like you go down a rabbit hole once you start looking for small corrections to the simple answer, right? Because it's never ending. But the fact that that Richard Feynman got close enough to made the two numbers agree nearly exactly, gave him confidence that there was nothing wrong with quantum mechanics. That you just had to work really hard if you wanted to get that extremely accurately.
Feynman, who was a sort of all-around kind of person, played bongo drums in an ensemble that he was with and other things. But his recreation during the war, when he was in Los Alamos, was to wander around Los Alamos and actually open all the safes.
Safe cracking, it was a side.
Which he was successful at.
Thank you so much. Thank you again, John.
Thank you for coming.